Lesson 4.3 is another type of distribution. Last lesson we looked at a uniform probability distribution. Today we're going to look at one called a binomial probability distribution. This is one that is very common that we are going to refer back to again later in this course. Again, it's just to recap what a probability distribution is. Remember, it is all the different probabilities associated with all the different outcomes of a particular event. So binomial probability distribution in particular, bi indicates that there's two possibilities happening. All right, so again, this is the specific type of probability distribution, binomial. Sometimes it's called a Bernoulli trial. Just in case you see that in any of the notes, I will refer to it as binomial probability distribution though. So what's special about this one, what separates it from some other ones that we're going to look at, is that it involves independent trials. Okay, so let's just take a second to remind ourselves of what independent trials or independent events means for us, because that's going to be really important. Independent events are ones where each event, each trial is not affected by what's happened before or what's going to happen after, obviously. It has no effect on what's going to happen after. So a great example of independent events is when we roll a die. Every time I roll a die, I have a 1 in 6 chance of getting any one of the numbers on the face. Flipping a coin is another example of independent events. Again, every time I flip the coin, it's a whole new ball game, and so I don't have to worry about what's happened before. Whereas dependent, just to contrast that, would be things like pulling cards from a deck without replacement, or pulling some sort of anything out of a bag without replacement. So if I deal out a card, and let's say it is a heart, then if I don't put that card back in the deck and I pick another card, that means my probability of getting a heart on my second card is different, or it's going to be less, because I've already taken one heart out of the deck. So those are dependent trials. That's not what we're dealing with today. So we're dealing with the ones like flipping coins or rolling dice, or anything that follows that type of can't think of the word I want, but anything that follows that type of pattern. All right. So the other thing is that the outcomes can be measured as either success or failure. All right. Success or failure. So there can be different outcomes, but we need to be able to classify them. We need to be able to put them into one or of two categories. We need to call it either success or failure. So again, let's go back to rolling a die. Yes, there's 6 different outcomes, but if I phrase it in a certain way, I can make it success or failure. If I roll a die and I say that I'm looking for the number of 6s that come up, then I could call getting a 6 success, and I could call getting anything else a failure. So as long as I can put things into one of these two categories, if I can frame it in that way, then I could use the binomial distribution. So both of those things are really crucial to what we're going to do today. So this idea of it being independent, and this idea of being able to frame it as two separate outcomes, success or failure. That then what follows is that the random variable, which we've learned about and talked about over the past couple of lessons, is the number of successes in a given number of trials. So that is our random variable. So all we're looking for is we're going to count up how many successes we had. Again, if I was rolling a die and I was looking for 6s, say I rolled a die 10 times and I want to find the probability of rolling 3 6s, well then I would I can calculate the probability of that again as success or failure. So the probability of X successes in N identical trials is given as P at X, probability of X, equals N choose X. So we're using combinations in this one. So what we learned in the last unit about combinations is going to come back. So N is the number of trials. So if there was 10 rolls of a die, then N would be 10. And X is the number of successes that we're looking for. So it's N choose X. P is the probability of success as a decimal. So if there was a 30% probability of an event happening on a single trial, then P would be 0.3. And then Q is the probability of failure. And you can see that we're going to use powers for that. So P to the X and Q to the N minus X. Again, X and N are going to be specific numbers for any particular one. So we need to know what P and Q stand for as well. So we got a few variables going on, but it's actually pretty easy to use this formula once we wrap our heads around what the variables stand for. Note that P plus Q must equal 1. Again, that's the equivalent of saying that the probability of success plus the probability of failure equals 100%. Of course, that needs to be true. Each term in the expansion of P plus Q to the N represents the probability of one possible outcome in the probability distribution. So that may look kind of familiar. It should anyway, because that is relating to the binomial theorem that we talked about in the last unit. We don't need to actually use the binomial theorem. We don't need to expand it out, but if we did, then it would relate to all the different probabilities that we are going to put together in the distribution. So if you look back at this formula, let's just put a box around the actual formula, because that is really what we need to focus on here. Let's try again. There we go. So what I just put a box around, that is the formula that we're going to use. So look at that and think about, that's actually one term in the binomial expansion. Let me just go back to the binomial expansion for a second. I guess I need to look here. Give me 1 second. Binomial expansion. So remember this, right? Here's a binomial expansion. And so we have, 4 choose 0, a to the 4, b to the 0, plus 4 choose 1, a to the 3, b to the 1, and so on. So the formula that we're looking at today is just one term. So it would be the 4 choose 0, a to the 4, b to the 0 part. And then the whole distribution is all those terms added together. So that's the connection between these things. That's why it's a binomial distribution. All right, so again, it's not hard to use once we get familiar with all the different variables and so on. So let's see how it works out. 2 standard dice are rolled 5 times. Calculate the probability distribution of rolling doubles. All right, so first off, as I read this 5 jumps out at me. That is the number of trials. So number of trials and that means that it's actually the variable n. So 5 would be our variable n. Probability of rolling doubles. Okay, so that's what we're looking for. So to identify a random variable, we need to know that's going to be the number of doubles rolled if we do 5 trials, if we roll a pair of dice 5 times. So x equals number of doubles. Again, we're rolling a pair of dice 5 times. How many pairs of doubles could I get from that? Well, it's quite possible that I would, in rolling the pair of dice 5 times, I wouldn't get any doubles, right? So maybe I'd get 0. That's a possible outcome, 0 doubles. Or maybe I get 1 pair of doubles, or 2, and so on, up to a maximum of 5. Why do I stop at 5? Well, because I'm only rolling the dice 5 times. If I roll a pair of dice 5 times, it's highly unlikely I'm going to get 6 pairs of doubles. Something funny is going on. So it could be anywhere from 0 to 5 pairs of doubles that I can roll. So those are my outcomes, and that's x. Let's just go ahead and put that in here. That's my random variable, 0, 1, 2, 3, 4, 5. So this table is already set up with enough rows to fill that in. So what else am I missing? I've got n and I've got a bunch of different values that I can put in for x. I need to know what p and q are. I need to know the probability of success on an individual trial. That part's important. I didn't gloss over it, but I want to go back and highlight that again up here in the definitions. P is the probability of success in an individual trial. And same as Q is the probability of failure on an individual trial. So what's my probability of rolling doubles if I roll a pair of dice 1 time? If you've forgotten, we can just make up our table that shows all the outcomes for rolling a pair of dice. Let's just zoom in on this so I can write it a bit neater. Doesn't take very long. Okay, so this is die number 1, die number 2, die 1, die 2. So if I get a 1 and a 1, I get a 2. 1 and a 2, I get a 3, and so on. We've seen this lots of times already, so this is nothing new to anybody. I'm just going to fill this in. It'll take me about 20 seconds or so. All right, so my doubles come from doing a 1 and a 1, a 2 and a 2, a 3 and a 3, and so on. These are all my doubles. I think that you probably didn't need this visualization to know how many different types of doubles we could get. Obviously, there's 6 sides to a die, so there's 6 different ways we could get doubles. However, we also have to know, to get the probability of getting doubles on a single roll, we have to remind ourselves of how many outcomes are possible. So this table shows all the possible outcomes. If you remember, there's 36 outcomes from rolling 2 dice. They're all represented here. So of those 36 outcomes, 6 of them are rolling doubles. So the probability of getting doubles any time we roll a pair of dice is actually 1 in 6. All right, so P is going to be 6 over 36. But as I said, that reduces to 1 over 6. So that's actually our probability of success on a single trial. So that's what we need to know. Q is our probability of failure. I'm sure that instinctively you could figure that out. You know that it's going to be 5, 6, but just to show it mathematically, all probabilities add up to 1, and since there's only this or that, success or failure, anything that's not doubles is considered failure, so we do 1 minus 1/6, which equals 5/6. So we need to know these 2 values as well. All right, we're going to use these in our formula. So that will let us do P at x. So the formula, again, is for P at x, the probability of any one of these events happening. So the probability, P of x, of getting 0 doubles, the probability of getting 0 doubles, if we put that together with the formula, remember it's n choose x, p to the x, q to the n minus x. So n was 5. X is 0 on this row. Probability of success is 1/6, and that goes to the exponent x, which is 0 again. Probability of failure is 5/6, and that goes to the exponent n minus x. So 5 minus 0, so probability 5. So again, this should look really familiar from the binomial theorem that we looked at. So that's how we're going to calculate the probability for getting each one of these. I know that in the past I've used that third column here to show what x times p at x is, but I think I just want to use that space to actually get a decimal answer here. So if I were to type this all in to my calculator, 5 choose 0 times 1/6 to the 0 times 5/6 to the 5, that works out to 0.402. What that means is that my probability of getting 0 doubles when I roll a pair of dice 5 times is about 40%. And then if I do the exact same thing for getting exactly 1 pair of doubles, all it changes is the x value in the formula. So it now becomes 5 choose 1, 1/6 to the 1, and then 5/6 to the 5 minus 1, which reduces to a 4. And when I work that out, that also happens to work out to 0.402. So it turns out that we have the exact same probability if we roll a pair of dice 5 times of getting either 0 pairs of doubles or 1 pair of doubles. And together they make up 80% of the overall probability. So we know that as we go up, we're going to have less and less likelihood of getting more pairs of doubles. All right, so let's just fill in the rest of it. 5 choose 2, 1/6 to the 2, 5/6 to the 3. And that one works out to 0.161. So the probability's dropped off significantly of getting 2 pairs of doubles. Getting 3 pairs of doubles, we can expect it to be even less. This should be a 3 up here. 5/6 to the 2. That works out to be 0.032. So we have a 3% probability of getting 3 pairs of doubles. We get a 0.3% probability of getting 4 pairs of doubles, and that doesn't leave much for getting 5 pairs of doubles. But of course, logically, we wouldn't expect to roll 5 pairs of doubles when we roll a pair of dice 5 times, would we? I mean, that just instinctively, I think we would say, well, that's not very likely to happen. We wouldn't bet much money on that. And we'd be right. The probability is 0.0001, or 1/100th of 1% probability of getting 5 pairs of zeros. All right, so that's the probability distribution. If you add up all of these probabilities, we got 40 plus 16%, that's already 96%, plus another 3%, there's 99%. Then I'm not even counting the decimals or parts of percents. You add it all up, it adds up to about 1 or 100%, within rounding error. So, what does P at 5, I'm looking at, actually let's look at C, that's what I just answered. Calculate the sum of the probabilities in the distribution, so they approximately equal to 1 because that accounts for all the probabilities. What does P at 5, D part, tell us? Well, that tells us the probability for one particular outcome, the outcome of trying to figure out getting exactly 5 doubles. Construct the probability histogram. Okay, sure. Well, our highest probability is about 40%. Looking at this graph here, I guess that means I will need to go up by 0.1s or 10% at a time. I don't have enough room to... sorry, I take that back. I think I can go up by more. So I'll make this, every double one will be a 10%. So there's 0.1, 0.2, 0.3, 0.4. All right, and again, that's P at X. X would be my different possibilities. So my possibilities were 0 through 5, right? 0, 1, 2, 3, 4, 5. And then I can make bars to match what the height is. So 40.2% would go here. And that's actually for my first 2 bars. I'm going to cheat and do them both at once, and then just draw a line down here. So those are my first 2 bars. And then I had what? Then I had 16.1% probability of getting 2, so that would be here, approximately. And then I had 3.2%, so that's going to be way down here. And then I had less than 1%, which would be down here. And then basically nothing for 5. So it's barely going to be a bar at all. Here's my probability histogram. Color it in so it stands out a little bit more. I don't know if I can... There, that's the best I can do. Let's make it into a probability polygon. So I'm just going to connect the tops of each of these bars together. The polygon is going to look like this, or the shape of it anyway. The shape of the curve is going to look like this. Do you remember what we called that type of distribution? It's called right skewed, and because the tail is on the right hand side. So that was part F. Now we want to calculate the expectation and interpret its meaning. That's the last part. So going back to the formula for expectation that we had from the first lesson of this unit, we're going to do x times p at x. So first x was 0, and the probability of getting 0 pairs of doubles would be 0.402. And then we would do 1 times the probability of that, which was 0.402 again, and then 2 times 0.161, and 3 times 0.032, and 4 times 0.003, and 5 times 0.0001. 5 times 0.0001. When I put all that into my calculator, work out what that is, it comes out to approximately 0.832. So, what does that mean? Well, this number, 0.832, means that on average, we would expect less than 1 pair of doubles for every 5 rolls we do. In fact, if we roll a pair of dice many, many times, then the average number of pairs of doubles that we would expect for each set of 5 would be 0.83. So the closest that we could round this to is, if I had to make my best estimate for the number of pairs of doubles that I would expect, would be 1. But this is number of pairs of doubles on average. All right, so that's the basic idea as far as that goes. I'm going to do a couple more examples. I'll go through them a bit more quickly now that we've done one in detail, but that's the idea. Of course, we have expectation. Again, I just calculated the expected value, but just like for uniform probability, there is a shortcut, and that's what we have here. When determining the expected value for a binomial distribution, you can multiply the number of trials, n, by the probability of success for an individual trial instead of using the standard process. In other words, the formula I used above. So let's just confirm that for what the one we just did. So remember, for the previous example, n was 5 and p was 1/6. So the expected value would be 5 times 1/6, and that works out to 0.833. Compare that to what we had above, it's the same, right? So the expected value is exactly the same, well, within rounding error. So we can see that our shortcut is fine, it's going to work. Okay, so now we have a nice, easy way to get the expected value for binomial distribution. Okay, let's see a couple more examples though. About 11% of Canadians are left-handed. If there are 24 people in this room, determine the probability that exactly 2 of them are left-handed. So we can use the formulas that we already talked about. We don't have to calculate the entire probability distribution. We can just calculate part of it. So part A is like calculating one row of a probability distribution. We just have to know what we're dealing with. So we're looking for people who are left-handed. So being left-handed is success, right? So we're counting this. We're counting left-handed people. So every time I find a left-handed person in this experiment, I've been successful. So x is, the random variable is number of left-handed people. And in this case, we're looking for 2 of them, so we want to find an x value of 2. So that's what we have in this case. We need to know what n is. All right, well, that's no problem. There's 24 people in the room, so that gives us our n value. And we need to know p and q. Well, p is there's 11% of Canadians that are left-handed, so we would expect that we'd have 11% probability of getting a left-handed person anytime we randomly select one. So p is 0.1, and that leaves q to be 1 minus 0.11, because they always have to add up to 1, so 0.89. So we need those 4 variables in order to do the calculation. So the probability that 2 are left-handed, that x equals 2, let's write it that way, x equals 2, is going to be 24 choose 2 times 0.11 to the 2 times 0.89 to the 24 minus 2, which is 22. And that works out to be 0.2 257, or 25.7%. What is the probability that at least 2 of them are left-handed? Okay, at least, that important term again. That means that really we're looking for 2, 3, 4, 5, 6, and so on, up to 24 of them being left-handed. We could calculate each one of those directly and add them all together, but that would be a really big task. This is a case where it would be a lot less work to use the indirect method. In this case, if we just calculate how many people, or the probability, I mean, of having 0 people, coming up with 0 left-handed people, or 1 left-handed person, then it would be a lot less work, and I could subtract that from 1. So, again, it's really 1 minus the probability that x equals 0, and subtract also the probability that x equals 1. And then that'll leave all the rest of them. The probability that I get is the probability that x is greater than 1. So that equals, if I just do it all at once here, that equals 1 minus 24, choose 0, times 0.11 to the 0, 0.89 to the 24. And then the next part is 24, choose 1, 0.11 to the 1, 0.89 to the 23. Put all that in the calculator, I get, for the first one, when x equals 0, I get a probability of having no left-handed people out of 24 is about 6%. And the probability of having 1 left-handed person out of 24 is 18% approximately. So when I work it all out, it turns out to be 0.758, or approximately 76% probability that at least 2 of the people out of 24 are going to be left-handed. So that makes sense again, right? If there's 11% probability any one of them is going to be left-handed, and there's 24 people in the room, just some simple math tells me that I would expect about 2 or more. So let's actually do the expected value, though. And again, we have that really simple calculation. It's kind of intuitive, in fact. You get x equals n times p. N we saw was 24. P was 0.11. That works out to be 2.64. So every time I take a group of 24 people and check them to see if they're left-handed, if I do that over and over with a whole bunch of groups of 24 people, I would expect on average to have 2.64 of them be left-handed. So the expected number of left-handed people in the room. This many on average. Okay, last example for this lesson. I feel like it's been going for a while, so you'll be happy to know we're almost done. With a certain set of atmospheric conditions, the probability of rain is 40%. All right, so as soon as we see that, hopefully we already start thinking in terms of, well, what's that going to be? Well, if we're measuring probability of rain, and that's going to be our success, or that's what we're going to define as success, right? So that's going to be our p-value. During a 1-week period with those conditions, what is the probability that it rained on fewer than 2 days? So that's really similar to what we were asked for in part, kind of similar anyway, to what we asked for in part B of the last example. Except instead of finding that it was at least 2 days, we want the exact probability that it was fewer than 2 days. So we're not going to do it indirectly, but we are going to find the probability that it rained on 0 days, the probability that it rained on 1 day. And then just add them together. So the probability that it rained on 0 days, we need to, I guess, identify a couple other terms or a couple other variables. For 1 week, we can interpret that to mean that n equals 7. And x, of course, is 2, or sorry, 0, I've already identified that. And of course, q, I guess, is the only other thing I haven't written down. That's going to be 1 minus 0.4, 1 minus 40%, so 0.6. So there's everything I need. So 7 choose 0 times 0.4 to the 0 times 0.6 to the 7. That works out to be 0.028. So that's the probability. There's about a 3% probability that it's going to rain not at all if any one day has a 40% probability. The probability that it rains 1 day out of the week is going to be 7 choose 1 times 0.4 to the 1 times 0.6 to the 6. So again, we make x 1, and that changes the two exponents plus the one number that comes after the c. That's a higher probability. That one works out to be 0.131. So the probability that is fewer than 2 days is going to be 0.028 plus 0.131. Just add those two together, which equals 0.159, or about 16% probability that it rains on less than 2 days. What's the expected number of rainy days for this week? E at x equals NP, 7 times 0.4, 2.8 days on average. Well, actually, let me just rephrase that. Maybe I won't say on average. Our expected value on average would be 2.8, but in this case it's asking us what's the expected number of days for this week. So if someone said to me, based on this information, how many days would you predict we're going to have rain this week? Well, then I'd round it to the nearest whole day, and I'd say we'd expect 3 days of rain this week. And that's it for now.